Hello students, welcome back. Let us resume our discussion in section 2. We'll try to complete it with this video. We have one more topic to go. It's a special case, modular prime. Previously, we went through the main theorem and the corollary, and they're both based upon modular m, where m is an arbitrary positive integer. But in a special case, when m is a prime number p, then this GCD is gonna be 1 because, we have a prime number here. Oh, excuse me, not always 1. Sorry. If A is a multiple of P, then of course that's different. Otherwise, GCD is 1, so we don't really have to consider the top line. And then always we can get a unique solution, modulo P. Still, you have to consider the special case on back of my mind somewhere when A is divisible by P. Okay, let's begin. An integer is invertible if and only if it is not divisible by P. Oh, it's showing up already. It's not like putting that at the back of your mind somewhere, but it's coming right up front. Not divisible by P. So you see here in this kind of example, GCD is 1. That's coming up front. So let's see. Let me copy and paste this thing here. So put P here, and then P here, and then P is prime. So what do you mean by GCD of A and P is 1? P does not divide A. So this and that are equivalent. So the only way GCD of A and a prime is non-trivial, something other than 1, of course it should be P, and the greatest common divisor of something in P should be either 1 or P, and if P does not divide A, then it's 1. If P divides A, then it's P. So maybe P does not divide A. And then let's copy and paste this thing again. Okay, let's look at this again. GCD is 1 if P does not divide A. You see, GCD is a common divisor, and it must divide P. So it should be either 1 or P. So P does not divide A, then GCD is 1. P does divide A, and it's P, because, P divides A as GCD means P divides A. You already went through this. So keep those in your mind. And then let's try to set up and prove it. An integer is invertible if and only if it is not divisible by P. There you go. A times something is 1. That means it's invertible. A is invertible. Multiplicative inverse exists if and only if P does not divide A. But this can be rewritten modulo P like this. P does not divide A is same as P is not congruent to 0 modulo P. Is that clear? P does not divide A means the remainder is not 0 when I divide A by P. And that's precisely what this is. Remainder is non-zero. But if you look at it in a second viewpoint, this is something we had been using for a long time, don't you think? There exists the multiplicative inverse, 1 over a, if and only if a is non-zero. This is something we have been using for rational numbers, real numbers, even complex numbers. Denominator should be non-zero. Remember this? We have been using this for a really, really long time. And we are trying to establish something similar to that, but of course, it's a bit higher up. We are doing it modulo prime. Does it work modulo any m? The answer is no, actually. Modulo prime, that's important. And we're going to go a little bit deeper into this in abstract algebra. Here, we'll just do this and then move on, and then a couple more. Okay, let's prove it. This is necessarily sufficient. So we have to prove both ways. So step 1 is the forward direction. We'll assume there is multiplicative inverse and p that divides a, or equivalently speaking, we can prove the counterpositive. Assume p divides a and prove that there's no multiplicative inverse. That's what you're going to do. We're going to prove the counterpositive. We'll assume p divides a. So p divides a, so a is p times something, integer, means a is congruent to 0 modulo p. Then for any b, a times b is congruent to 0, and that cannot possibly be 1. That completes the proof. P divides a, then a is congruent to 0. So a times b is actually 0 times b. Yeah, a times b is 0 times b, so it's 0. Yes. There you go. Now, how about the inverse direction? Suppose that p does not divide a. In that case, there's an inverse. Well, if p does not divide a, that means that GCD is 1. So we can use 2.3. GCD is 1, so the multiplicative inverse exists. We have a unique solution of that modular equation, linear modular equation, linear congruence equation. So, we have it. An integer is invertible in terms of multiplication if and only if it is not divisible by p. How about the next problem? There's no non-trivial zero divisor modulo p. What do you mean by non-trivial zero divisor? That's what it means. A times b is 0, then either a is 0 or b is 0. 0 divides 0, yes, that's true. 0 times anything is 0. But there's nothing else. Two non-zero numbers multiply and then end up 0. That means those non-zero numbers divide 0. But we already know that that's not the case. 0 is divisible only by 0. That's for the usual multiplication in the set of integers. But similar thing applies if you consider congruence modulo p. Now, if you use modulo m, that's not always true. For example, 2 times 3 is 6. and that can be 0 modulo 6. Neither 2 nor 3 is 0, but 2 times 3 is 0 modulo 6, and the reason because we have something like that is because this is a composite number. For prime numbers, that's not going to be possible, and we are set out to prove that. How do you prove it? Well, one direction is obvious. If a and b are both 0, then a times b is clearly 0 times 0, so it's 0. So we only need to prove the forward direction. Am I making sense here? If both a and b are 0, then a times b is clearly 0, so let's assume the other case. A and b are non-zero. In that case, what do? Two non-zero numbers, we can multiply the multiplicative inverse, which exists because of part A, and multiply by multiplicative inverse here, here, and then what do you have? This thing drops out, and A inverse times 0 is 0, so B is 0. That's a contradiction because we assume B is non-zero. Neither A nor B is 0, that was the assumption. So the proof by contradiction works. There's no trivial zero divisor, modulo P. Modulo composite, it doesn't hold, but for prime number, it works. How about C? That P be a prime, then every non-zero integer is an inverse of itself if only if it is congruent to positive 1. This is wrong. It's not every. A non-zero integer is an inverse of itself if and only if it is congruent to plus or minus 1. Sorry about that. This is correct version. It doesn't have to be every. Okay, how does that work? A times A is 1. Yes, inverse of itself. So A times A is 1. That means A is either 1 or negative 1. That's what this thing is talking about. If we take the square root of 1, we have plus or minus 1. So it looks like it is working in R, or also in Q, and also in C, in those number systems, but does it work modulo P is the problem. What do you think? Well, you can do it like this. You can set up a squared minus 1 and factor it. And then what do you have? We already proved that there is no non-trivial zero divisor. So something times something is 0, one of them has to be 0. Either a plus 1 is 0 or a minus 1 is 0. There's no way I'm going to get 0 by multiplying two non-zero numbers modulo prime. Modulo composite, that's different, modulo prime. So the conclusion, A is congruent to negative 1 or A is congruent to 1. Negative 1, which is congruent to actually P minus 1. Okay, that completes section 2. And we're going to meet again in lesson 7 and continue on with section 3.